Welcome back, everybody. I hope the sound is okay. And I obviously hope you had a great weekend, although we are back to winter time now. I've actually hid my winter coat and I have to fetch it back again. So let's hope this weather changes swiftly. Now, what I want to give you is first the overview of this week, and then some additional messages. And this deals also with the final project. So today we are going to, if you thought this kind of Lagrangian formalism was cool, today we're going to do something which is even better. We are going to add constraints. And that means that you can develop the equations of motion, for instance, for the mathematical pendulum, which often is a kind of hassle when you're setting up the forces, decomposing them properly, etc., etc. So this is one of the things which we will derive today, the equations for the mathematical pendulum, using the Lagrangian formalism with constraints. And that's also very powerful mathematical machinery, which you can use for other problems than just problems in physics. So if you have a constraint on a specific system, you can actually set up a Lagrangian with some additional parameters. And then taking the derivative of this Lagrangian, you can then find the equations of motion, which optimize a specific problem. So that's an extremely powerful machinery. Now, and we are going to use these last 2 weeks also to sneak in repetition. So the kind of examples we are going to pick up are things you've seen before, and we're just going to use them to repeat what we have gone through during the semester and put that in a, how to say, with a Lagrangian formalism at a higher level. And I also wanted to say a little bit about the end of the semester. And we have this homework 9. And if you just scroll down for the weekly information which we have, there is an additional homework 10. So the last 2 homeworks are basically paper and pencil exercises. We haven't plugged in anything numerical in them. Homework 10 is just an optional in case you feel that you would like to have some more points, some more score. So that gives you actually an additional score of 10% on top of what you had. And since homework 5 was not included in these canonical 9s due to the sad happenings, if you have done it, or if you want to do it, you can add that score on top of what you had. So suppose you ended up with 800 points on 8 homeworks, which gives you a score of 100. We'll divide by 8. If you then add another 100, you would have 900 divided by 8. So that gives you additional score on the final score. So everything is just added up, what you have done. So if you have more, that simply adds up and can then compensate if something went wrong in one homework or in one of the midterms. So there's always the possibility to make up, if you're interested, obviously. What we also need some input from you guys is about the final. So the final is going to be hopefully a little bit less work than we had with this midterm, which, well, I like it because the solar system is a fun thing to do. But we typically, what we have done is to present it roughly in the middle of next week. And we have a deadline by May the 5th, the end of the exam period, the finals week. And one of the reasons why we're going to be a little bit pickier with the deadlines is that we have to punch in the grades by, I think it's May 8 or May 9. So we do also have a hard deadline. That means that we are going to be a little bit less flexible. You probably have known me now by what I mean with flexibility, with deadlines and things like that. So there's always some flexibility, but we have to grade them by May 8 or May 9. So it's important that we try to wrap up in time. So I'm going to put a deadline on May the 5th, but there's also always the possibility of some flexibility in case things go wrong. And hopefully we can have it by the middle of next week or earlier next week, so you can have some time to look at it. But please feel free to come with some feedback and inputs about timing, deadlines, and so on. And we can try to adjust that to your schedule as well. Any questions about the last week's practicalities? Okay, so what I want to do now is basically whiteboard work today. And we are going to go through Lagrangian formalism with constraints, which is going to give us an additional powerful tool to derive the equations of motions. So there will be some mathematics, but then you will see that when we attack a problem like the mathematical pendulum, it's much easier to derive the equations of motion. And it's actually pretty cool. So let me try to convince you that this is fun. Okay, so I'm going to switch over to the whiteboard. And so let's do that as quickly as possible. So what we have been doing now is to present this Lagrangian formalism. Oops, what happened here? There we are. So in the Lagrangian formalism, what we did was to use this principle of least action. So we want to minimize, I'm just repeating quickly what the kind of ingredients which we are looking at, principle of least action. So we want to optimize typically an integral of this type from some integration limits x1 to x2. And there is a function which we sometimes call the Lagrangian. And this will depend on some quantity y, the derivative of y, and this can depend on x, so it can depend on time. So we want to optimize this quantity here. What we have done is also to introduce a Lagrangian. And with that one, we can derive the equations of motion. And this is given by the kinetic energy minus the potential energy. And if we're just staying in one dimension, this is a quantity which is given by 1/2 of m of v squared minus some potential which depends on x. Then what we did was to use variational calculus, and we derived what is called the Euler-Lagrange equations, variational calculus. And then we could derive the Euler-Lagrange equations. And I'm saying equations because we can have more than one types of variables. And these equations, if you stay in one dimension, they are given by the derivative of this function, the partial derivative, times or minus the time derivative of the partial derivative with respect to this v dot, the velocity. Sorry. Sometimes the v. And now we have assumed that this Lagrangian is a function of position, velocity, which is a derivative of position, and time. That's a basic assumption we've made. So in general, if we want to be a little bit more general, this is often written in terms of general coordinates. So we could define some general coordinates. And in that particular case, we let x, which we have here, go over to a general position q, or just it's normally called a general coordinate. And then we can let v go over to the derivative of the q. And this is normally called a general velocity. And if you multiply that with mass, you would have a general momentum. And if we look at one of the examples we've seen till now, we've had a typical example where we went from Cartesian coordinates to polar coordinates. So we went over to r and phi. So this is a comma. And then we had a Lagrangian, which was given in terms of x derivative, the velocity in the x direction, the position in the y direction, the position in the t direction, in the y, the derivative or the position in the y direction. And this was given now in terms of r, the radial velocity, the angle, the angular velocity, and t. And this could normally be, this is normally written out in terms of general coordinates. We would have a sum from 1 equal to 2 of L of some Qi of Qi derivative and t, where now Q1 is equal to R and Q1 derivative is equal to R, the radial velocity, the derivative of that one. And Q2 is given by the angle, and Q2 derivative is then given by the angular velocity. And then for these specific variables, for each one of these, we would have a set of equations which we solve, where we have the derivative with respect to Q of I, one given I, minus d dt, where we have dl of dq of I prime, and then we have I equal 1 to 2 here. So you can easily generalize this to a general coordinate and a general velocity, where then the coordinates and the velocities, they refer to the specific system which are looking at. So this is so far as we have the kind of formalism which we have developed. And last Wednesday, we derived the Euler-Lagrange equations. What we're going to do now is to set up these equations with a constraint. And when you have a constraint, that means that one of the variables depends on the other one. So that means that if you have a constraint on R, it means that phi could be the free variables, and R would then be defined by phi. So instead of having two free variables, R and phi, you would have only one of them, and there would be a constraint. And this is going to give us an additional powerful tool by which we can actually derive the equations of motion for many interesting physical systems. So let's take a look at the addition of a constraint. And the best way to see that is actually to look at a simple example from mathematics. So we have a function in 2 dimensions, and then we are looking after the solution. We want to minimize this function with a constraint that the values should be on a specific line. So that would be a typical problem with a constraint. So let's take a look at the variational calculus with constraint. So suppose now you're given an example, and let's just call this an example 2 here. Suppose somebody gives you a function and you want to optimize this function. So we want to minimize, this is the task we are given, minimize a function f of x1 and x2. So it's a 2-dimensional function, and this is something which I just made up. Minus 3 times x1, minus 6 times x1, x2, minus 5, x2 squared, and then there's a plus 7x1 plus 5x2. So we want to minimize that one, subject to a constraint. To the following constraint. And the constraint is that x1 plus x2 is equal to 5. So what that means, if you want to make a graph here, you can set up a graph for x1 and x2 here. So we have 1, 2, 3, 4, 5. So we know then that when x is equal to 5, then obviously x1 equal to 5, then x2 has to be equal to 0. And you can see that immediately, right? So that means that this is the point we have. And then we see that if x1 is equal to 4, then x2 has to be equal to 1. So that means we get this point. And since this is just a straight line, we see immediately that if x1 is equal to 3, then x2 has to be equal to 2 here. So this goes like a line. So, okay, this you see again my fantastic drawing capabilities. Just imagine again, this is a straight line, okay? So the solutions are now going to be on this line here. So the points which we find, x1 and x2, when we minimize the function f, they are going to lie on this line here. Now, this is a problem which we can solve without introducing anything which has to do with the Lagrangian formalism. But when you get more complicated functions, you will see that this Lagrangian formalism is extremely powerful. Now here, we can simply substitute x2 is equal 5 minus x1 and put that back into the equation for f. And then we can take the derivative of f with respect to one of the variables, and then we find the minimum. So let's do that first, because that's the simplest possible way we can deal with this function here. So in this particular case, what we end up with is simply replacing x2 with 5 minus x1 in the function f of x1, x2. And then we take the derivative with respect to the variable which we have. So if I do that, I can now replace x2. What I get then is just that fx1 of x2 goes over to a new function, which I'm going to call for h of x1. And that's simply minus 3 of x1 squared. And then I have minus 6 x1. And now I'm putting in 5 minus x1. And then I have minus 5. And this is the value of x2 squared. And then I have plus 7. This is exciting, isn't it? But let's go through the math here so that we can find the solution of minus x1. And this becomes equal to minus 2 times x1 squared minus 22 times x1 minus 100. And then we want to minimize. So we take the derivative of this function h with respect to x1, and we want to minimize it. So this is the same as minus 4 times x1, and then minus, there should be a plus 22, I think. Yeah, there's a plus 22 here. And then we get plus 22, and that means that x1 is equal to 11 divided by 2. And I go back to the equation with x2, which is equal to 5 minus 11 divided by 2. So that gives us minus 1/2. So these are the solutions which we are searching after. And I guess this is not unexpected and pretty trivial to do, and you probably have done this before. Now, what we're going to do now is to reformulate this problem in terms of something which is called the Lagrangian formalism with constraints. So I'm going to take a top-down approach first, and then I'm going to derive the equations with the Lagrangian constraint. So you see where this term comes from, okay? So what we can do now, if we take this top-down approach first. So let's now, the top-down means that we have the equations. So I'm going to define a Lagrangian, which now is given by this function of x1, x2. But then I'm going to define a new Lagrangian, which is actually given by the previous one, plus a function here, lambda, where I have defined a function of x1 and x2, which is so that g of x1 of x2 is equal to 0. And this parameter which you see here, this is called a Lagrangian multiplier. And I'm going to derive this one in just some few moments. So now I'm just going to take a top-down approach and derive the same solution as we had previously. Now, this function, which I have defined, this g of x1, x2, which is equal to 0, is the same as x1 plus x2 minus 5. So that's the constraint which I have on the solution. That function has to be 0. That is the same as saying that the solution should be on this line, which I showed you just in some few moments ago. So how this can be derived, this L plus this parameter lambda times this function, is something I'm coming back to. So now I'm just using that one, and I'm going to use the Euler-Lagrange equations to actually find the same solution which I got by substituting and taking the derivatives. So this is a very common approach if you have a complicated function with a constraint. So has somebody here studied machine learning methods? Have you heard of something which is called support vector machines? That's one of the pre-2008 machine learning methods. Actually, that's based on you having a function L with a constraint. And then you optimize it. And you find the optimal parameters. That's actually support vector machines. What's the basic theory for that one? So all of this Lagrangian formalism is something which pops up if you enter the field of optimization. And a typical optimization problem we encounter in physics is a convex optimization problem. We have a convex function. We want to optimize it with some specific parameters, with some constraints. And that means that we're going to have a problem which can be formulated as we do now. So this is a much more powerful formalism because it's not only, limited to what we do in mechanics, but you can use it in many, many other types of problems. And if you take more advanced courses and you look at, let's say, optimization theory, which is a very popular topic in mathematics, or if you dive more into machine learning, you're going to encounter this way of formulating things. Okay, so let's take this kind of top-down approach and find the solution in the same way as we did before. So what we're going to do now is to use the Euler-Lagrange equations. So we have a d of L, and now it's this L prime of x1 minus d of d. And in this specific case, we have a Lagrangian which does not depend on this time variable, but we would have a dt here. If we add this one, we haven't specified that one. So we would have a d of x1 derivative of L, but x1 derivative is not defined in the function. So that means that in this specific case, we only have the first term here. And we should have a prime here. So this should be equal to 0. And then we can do the same with the second variable. So we need a d of L prime of dx2 here minus, and there's no dependence on this second parameter, and there's no dependence on the derivative of x2. So the second term in the Euler-Lagrange equations is going to be 0. So we don't need to worry about that. So if I look at the first term, the only one there which is different from 0 of dx1, this is the same as minus 6 times x1, and then minus 6 x2 plus 7. And now I have a dependence because I took this function which you see here, this lambda, and this is multiplied with x1 plus x2 minus 5. So when I take the derivative with respect to x1, I get a plus lambda here. And we want that one to be 0. So I can now reshuffle things. And you can see I can reshuffle x1 plus x2 and divide by 6. So this is going to be equal to 7 plus lambda divided by 6. Now, what we know is that x1 plus x2 is actually equal to 5. So I can use that. So this means that this quantity 7 plus lambda divided by 6 has to be equal to 5. And if I do the mathematics now, that means that lambda is equal to 23. So I found the value for this lambda. The next thing I do now, I take my d of this L prime with respect to x2 here, and that gives me a new equation, which simply reads like 6x1, and then I have minus 10 of x2 plus 5 plus lambda, and this is equal to 0. And I know as well that the x1 in this specific case is equal to 5 minus x2, that's the constraint which I have. I have found the value for lambda, which is 23. So when I then add everything in, so I have minus 6, and I have 5 minus x2 here, and then I have minus 10 x2 plus 5 plus lambda equal to 0. And I plug in the values, what I'm going to get then is minus 4 times x2 is going to be equal to 2 here. And that means that my x2 is equal to minus 1/2. And then I know that x1 is equal to 5 plus 1/2, and that is equal to 11/2. And these were the numbers which I found in the previous case where I did the substitution and I took the derivatives. So we're actually getting the same result. Now, the thing which I haven't done is actually to derive the equations with this Lagrangian multiplier, this constraint. So I'm going to take the kind of liberty now because I want to bring in a physics example. So I'm going to stay a little bit with this top-down approach. And then after I've done the next example, I'm going to derive this Lagrangian multiplier equation so that you see where it comes from mathematically. But I want to do some physics as well. So this was the mathematical warm-up exercise. We took a very top-down approach. I just gave you the equations without deriving them and said, now we use them. And you see that we get the same results. So let me show you the beauty of this formalism applied to a physics problem. And this is going to allow us to repeat some of the things which we did at the very beginning of the semester. So I'm going to wait a little bit with the derivation of, so if we go back a little bit, right now, I'm just presenting this one to you as a kind of black box. So I haven't given you the mathematics behind it. It's actually not so difficult, but let's use it again. So we are going now to have a physics problem. And this is actually one of these problems, which is a little bit tricky to derive if you just want to break down everything in terms of various forces. So this would be the example, I think it's example 4, or is it 3? Let's see now. Example 2, so this is example 3. Yeah? So this is normally what is called the mathematical pendulum. And we didn't derive it using the forces when we discussed harmonic oscillations, but it's actually in the lecture notes related to chapter 5. But let's now look at the problem here. So you can now think of this as being your x-axis. And then you have your y-axis here. This is y. And then we have the mathematical pendulum. So the mathematical pendulum has a stiff rod here. And this has a distance, which we call for r. This is the origin. And this guy here is just swinging back and forth here. And there's an angle phi. And then we obviously have if we now decompose it, there's a gravitational force here, G, right? So when you're doing the analysis, like we did in the very beginning of the semester, we would typically break this down in different forces. There would be some kind of tension force here, which we can call for T here. There's a gravitational force, and this thing is swinging back and forth, right? So before we move on now, so we are not going to analyze this in the traditional way. So if you remember back in the beginning of the semester, we set up this recipe where you would describe the system. So the system would be this pendulum, which is fixed to move back and forth. One assumption we have made here is that the length of the pendulum, and this is what normally defines a mathematical pendulum, the length of it is actually given by the absolute value of r, which we can rewrite as a little r here. So that's the length of the pendulum. And we assume that that stays constant. Okay, so we are not going to analyze this in terms of forces, but we need to set up potential energy and kinetic energy. So let me ask you now, what's the expression for the potential energy here? If you think of this object, this object which you see has a mass m, and we are not looking at the mass of the rod, but we're actually looking at the mass of this object here, which we give a label m. That's the mass of that object. So what's the potential energy which this object has? Yeah? Say again? Yeah, the potential energy. You can, if you take it in the XY coordinates, that's the easiest one. So stay in the XY system, the Cartesian coordinates, and you want to set up the potential energy for this system. Yeah. But if you think now, I actually cheated you a little bit because I put Y to be to go down. So instead of X, you would have Y, right? So the potential energy will be the mass of the object, the gravitational acceleration, times the position in the Y direction. Does that sound reasonable? So the only thing which acts on this system now is obviously the gravitational potential, and that's what sets up the potential energy for us. So we can set that up, and the rest is actually the kinetic energy. So if I want to set up the Lagrangian here, what I can do now is the following. I think this is a pretty nice way of analyzing a physics system. So if we now set up the problem, what we end up with, let me just write it down here. So we would have a kinetic energy, which is given by the mass of the object, the velocity in the x direction plus the velocity in the y direction. And then what we have next is actually the potential energy, which now is going to be a minus, and then we have a minus, so that becomes a plus here. And then I have an m times g times y. Does everybody agree on that? So the next thing we can do now is to transform to polar coordinates, because this is going to be more handy. So in our case, y is going to be given by r times cosine phi, and x is going to be given by r times sine phi. So that means that the potential energy is now going to change, because I can replace y with r times cosine phi. The other thing which I'm going to do now is, since I'm changing x and y to polar coordinates, to r and phi, you remember now that the kinetic energy is something which we rewrote in polar coordinates as the radial velocity. So we have an r dot squared plus the radius squared. So this is just a transformation of the velocities squared into polar coordinates, from Cartesian to polar coordinates. And then I get a plus, and then I have an m times g times r times cosine phi. But I said that this equation here, or this type of motion, has a constraint. So if you go back to the, let me just keep this up a little bit so we can set up the equations. I'm going to write a plus a lambda, this parameter, multiplied with a constraint. So if you go back to the physical system which we have set up here, what kind of constraint could you put on the system? Yeah. We keep the length fixed. So that means that L minus R has to be equal to 0. So that's a constraint. And you will see now, if we do that, we're actually going to derive the equations of motions immediately using the Euler-Lagrange equations. And if you were to break down everything in terms of forces, set up the right angles, it's very easy to make an error. Just ask me, because when I gave that lecture 2 years ago, I just messed up the angles. And then I said to people, hey, let's do this later with the Lagrangian formalism. So it's easy to get lost, even for this simple system here. And that's why this kind of formalism is so powerful. So we're going to put in a constraint which simply says that we require that R minus L or L minus R, doesn't matter which way you put it, L minus R, and we want this one to be 0. So that's the constraint which we have. So with those equations, I can now set up my equations of motion. And the thing I'm going to do now is to bring back the Euler-Lagrange equations. So I have the derivative with respect to R. I have the time derivative with respect to, and now this is going to be my modified Lagrangian. So I have to put a prime on it. So this is primed here, and it's primed here. And then I take the derivative with respect to R prime, and we want this one to be 0. So if I now do the derivatives, what I get is the following. So I'm going to get an equation which comes from this term, which goes like m times r times the angular velocity squared. I get plus m times g times cosine phi. And you can see that because when I go back to the equation, I have one term here, which gives me 2 times r divided by 1/2. Then I have the mass, and then I have this term, and then I get this term here. And then there is a velocity-dependent term, which simply gives me minus m times the second derivative here. And we want this to be 0. So this gives us now an equation. Oh, sorry, I also forgot one more thing here. And there should be a minus. I actually forgot that one. Because we get a minus lambda, which comes from the constraint, which we have here. So when I take the derivative with respect to r, I get lambda in here. So if we now look at this equation here, I can reorder it a little bit. I have plus m times g times cosine phi minus lambda is equal to m times the acceleration in the radial direction. Now, let me now ask you one thing. If you think back to the constraint which we have on r, what is the acceleration in the radial direction? Does r change with time? It cannot, right? Because we have said that r is fixed and it's equal to this length, which doesn't change. So that means that the first derivative of r has to be 0, obviously. And then the second derivative has to be 0. There's no velocity, there is no acceleration in the radial direction. So that means that we can now actually determine this constant lambda. So this has to be equal to 0. There is no velocity in the radial direction. So that means that I get lambda is equal to m times r of phi plus m times g times a cosine of phi. So guys, what is this lambda? If you look at lambda now, and you do a dimension analysis, what quantity does lambda represent? If you look at the terms which end as a cosine phi, it's just a number, right? But then you have m times g. So if you think of the dimensionality of this problem, what is that meant to represent? Yeah, that's a force. Actually, this force which you see here is going to be this kind of tension force which this object feels. So this lambda, you can actually show that, is going to be given by this guy here. So the force which acts on the object from the rod. So what you have here is actually a force. So we have actually constrained that force. So this is normally called a tension force, or the pull from the, or the effect of the rod on the mass itself. So this plays the role of a force. But now let's look at the differential equation in the angular direction. So what we do next now is we go to DOL of d of phi minus d dt, so this is L prime, of d dt of d of L prime, and then we take the derivative here, so the angular velocity, and we can then go back to the equation. Now there is, in this particular case, the constraint has no dependence on the angle phi, it's only two constants. Then we have a angular dependence here, and we have an angular dependence in here. So that means that one of the terms is going to give us a sine term. So if I take this term here, that one, this is going to give us a minus, and then I have an m times g, and then I have r times sine of phi. And if I take the second term, the velocity dependent term, that contains now a derivative with respect to the angular velocity, which we have here. So that gives me a 2 times a phi derivative multiplied with a half times m. And if I take the time derivative, then this is going to give me minus m. And then I'm going to have the term which runs like r dot, like this. And this has to be equal to 0. So if I do that, and just reshuffle here a little bit, so what I'm going to get, no, sorry, it's not r. It's, it goes like r squared multiplied with the second derivative of the angle. And then I'm going to divide with the r squared and divide with m. So what I get then is phi is going to be given by minus g divided by r times sine phi. And then I'm going to shift r to L. So this gives us simply an equation which we have seen in homework number 7. And this is given by minus g divided by L of sine phi, which is the same as minus omega squared times sine phi. And this is the same. So what we get now is phi equal to minus omega squared. Let me just rewrite it. Sine phi with omega squared is equal to g over L. And that's the natural frequency which we have. And the equation which you see here is the equation, one of the equations which we actually studied in homework 7 for the mathematical pendulum. And then you can add a air resistance, you can add an applied external force to it, but this is the way you would actually derive that type of equation in the simplest possible way, with the Lagrangian formalism. So you see the power here, you just start with the kinetic energies and the potential energy, and you have a constraint, and you end up with the equations which you could derive by setting up all the forces. And doing that, it's much easier to actually get a little bit lost, because sometimes you mess up angles and you misplace cosines and sines, and then it's always a hassle to find back or retrace back what you did wrong. So this is an extremely powerful way of finding the same differential equations which we have solved before. And if you make a small angle, then you know that sine of phi can be approximated with phi. And then you have the equation which has the standard cosine and sine solutions, or harmonic oscillations as we saw before. So before we do the mathematics, I wanted to show you another physics example and how we can actually use this formalism to find the equations of motions with a constraint. So I'm going to give you a new example and see if you now can think of what kind of constraints we would have here. So example 4. So this is one of these examples which I really hate. You've probably seen this zillions of times, and probably you have it in high school, perhaps even in kindergarten. I don't know. So we have the y direction, and we have the x direction, and we have an object which is sliding down on an incline here. Then we have an angle alpha, and we have an object which is moving down. And we have the gravitational force which acts down here. So we call this for just G. So again, what you could do now is to analyze this in the traditional way, as we did in the beginning of the semester. You find the forces in the X and the Y direction. But now we have a constraint here. So we have this object. We want to constrain it to move on the incline only. So it cannot leave the incline. So what kind of, how would you put the constraint here? If you were to put a constraint on X and Y, based on what I'm telling you now, that you want this object to be on this incline. It doesn't leave it, yeah? It's the angle. So the angle is constant. The angle doesn't change. So what kind of relation does that put on Y and X if you don't change the angle? There's one of these famous trigonometric functions which you can use. Say it again. Yeah, but if you take, there's another, so sine and cosine is a very good hint. But if you think of the ratio between Y and X, that's another trigonometric function. Tan, right? That's a tan alpha. So you have a constraint here, which you can express mathematically in the following way. So the constraint here, we could now define a mathematical function in terms of the following. So this function, this is a g of x and y. That's a constraint which we're going to put here. That says simply that y minus x times tan alpha is equal to 0. Because we know that y divided by x is equal to tan alpha. So if we now require that it stays on this plane, then this is a constraint we are putting on y and x. So every such physics situations or any type of this kind of optimization problems which we encounter, they can always be rephrased in terms of some constant. And when the function here is required to be equal to 0, this has a name in optimization theory. This is called a holonomic function. There are many of these names which I don't even dare to pronounce, but I have to actually look up because I once looked up what holonomic means, and I have to look it up again. It's an old Greek word. So if somebody can use ChatGPT or even Google or whatever and remind me of what holonomic means, then if we look at the equations, we can now set up the Lagrangian. So we have this constraint. We would then have obviously kinetic energy. And now we have x derivative plus y derivative. And now comes the potential energy. So I'm just going to put a question mark. And then we have plus lambda times this g of x and y. So I put the y axis to point up in the positive direction. So if you want to set up the potential energy, what should the potential energy be again here? It shouldn't be that different from the pendulum, right? mg times y, right? So that should be pretty obvious. So what we need now is simply, and since this points in the points downward, we get a minus. So we have minus m times g. So that means that what we get is actually 1/2 m times x derivative plus y derivative plus n times g times y plus lambda times g times x as a function of x and y. So what we're going to do next on Wednesday now is to apply again the Euler-Lagrange equations. And then we're going to find the equations of motion. So we're going to find the acceleration in the x and the y direction. And in this specific case, we can actually integrate up analytically. And analytical integration is going to give us the velocity in the X and the Y direction because they will be decoupled. And then when we integrate up the velocities, we get the positions again. And that's where we will start on Wednesday. And then we're going to derive the Euler-Lagrange equations with constraints. And thereafter, we're going to go through many more examples. And some of these examples may also be relevant for the final midterm or for the next two homeworks, which we're going to deal with, so that you get some hints and advice about. So homework number 9 has an exercise with the Euler-Lagrange equations. And there will be one exercise in the final one using the Euler-Lagrange formalism. Actually, that's much simpler than setting up the forces. Okay. If you wish to discuss things, midterm or whatever, feel free to hang around if you want. If not, we see each other on Wednesday.